America!
Here's an illustration from Alice in Wonderland, from one of the original drawings. And it's Alice, and she's sitting at the table with the Mad Hatter and the March Hare and the little mouse there at this tea party. Now, maybe some of you know, maybe some of you don't know, that the man who wrote Alice in Wonderland, his name is Lewis Carroll. That's his pen name. His actual name was Charles Dodson. And he was a friend of George MacDonald and Ruskin, a lot of famous people in the 1800s. He wasn't really a writer, though. He has become known for his writing of Alice in Wonderland than anything else, but he was actually an algebra teacher at Oxford University. When I visited Oxford, there were many tour buses that were decorated with the theme of Alice in Wonderland because they were celebrating the fact that their teacher was actually the writer of Alice in Wonderland. Now, if you realize that he was an algebra teacher and you read Alice in Wonderland, some of the passages take on more meaning, and one of them stands out for me, and let me see if I can pull up that text. Alice is there, and the March Hare says to her, "Take some more tea." The March Hare said to Alice very earnestly, and she responds, "I've had nothing yet." Alice replied in an offended tone, "So I can't take more." Now here comes the algebra teacher. "You mean you can't take less," said the Hatter. "It's very easy to take more than nothing." Now this to me seems like the sort of fancy that would happen for an algebra teacher like me. I've found that students have a lot of trouble when they translate algebraic expressions. Like, say we had the expression 5 more than a number. And we want to translate that into algebra. And we say 5 less than a number. Now remember, the March Hare said, you can always take more, but you can't take less. That's because if I ask students on a test to translate 5 more than a number, 5 less than a number, almost everybody would get this one right, because you can always take more. But usually without this kind of warning that I'm giving you right now, the majority of students would miss this one. So pay attention, because you don't want to be in that majority. You want to get both of these right. Now, when we translate English into algebra, I usually say take each word as you go along, and that usually holds except for this more than, less than, and I advise people to be on the lookout for that, the word than, even in both cases. You can be careless when it says more, but if you're careless when you say less, it's going to be wrong. The majority of students will start with 5, and then they'll see the word more, and they say, what does that translate? And it says plus a number. And if a student put this down on a paper, I would have to count it right. But they didn't really do it the best way. But let's look and see what happens if we use this second one. And please pay attention. This is going to be wrong. This is actually going to be wrong. So watch out. They do the same thing and go 5, and they come to less than. Less means negative, and then a number. I would have to count this as wrong. Because, now let's think about this. 5 less than a number. If you have 6 cows and you subtract 5, it's going to be 6, and you say 5 less than that. You're taking the 5 away from what you already have. So this sort of is an inverted sentence because you're taking 5 less. So the minus needs to be on the 5 because you're taking 5 less than a number. So I suggest that students write down the x, go less than 5, it has to be less than something. You could say 5 minus 5 plus x, and I would have to count that right. But this 5 minus x would be incorrect. So when you see this more than and less than, algebra students, the best thing to do is start with the number of things that you have and then say 5 more than that. Or start with the number of things that you have and say 5 less than that. And you won't miss half the problems. So let's pay attention to this warning about from Alice in Wonderland. And when you see less than and you say more than, let's do that one more time. So now if you see the sentence, let's do a different number. 14 less than a number, or 14 more than a number. I want you to see that less than and have that set off a warning in your head, more than. In both cases, let that word than set off an alarm and say, I have to start with the number. And then 14 less than that. Start with the number. And then 14 more than that. I think if you do both the more than and less than in this same way, and allow the word than to set off that alarm in your head, you won't make any mistakes. You can make a mistake on the more, but you can't make a mistake on the less and get it right. By accident, if it's more, if you went 14 plus x because of the commutative property, this is the same, but subtraction does not follow the commutative property. So when you have less, you must be more careful. So watch out for that when you're doing translating expressions. There's a story that I heard about Queen Victoria and Alice in Wonderland. I always used to tell this to my students. It has not too much to do with math, but it's kind of funny. Remember I said that Charles Dodson was a teacher of algebra at Oxford University. Well, when Queen Victoria ran across Alice in Wonderland, the story, she read it, and, being queen, she could do what she asked. So she told her attendants that she wanted every book that this man has ever written on my table at breakfast. And the next morning, she had a pile of books, all algebra. So be careful what you ask for. So Queen Victoria was a fan of Alice in Wonderland, and some of the websites say that she was a model for the Queen of Hearts, but who knows the mind of Lewis Carroll. He was kind of an interesting character. Anyway, thought you might be interested in knowing that. Well, here we're at the sub-menu of How-To software for Algebra with One Unknown, and we're going to look at translating expressions and open sentences. That looks like shrank the button too far. You don't get the last sentence. Translating expressions. Here you have a choice of working on expressions, which you would do at the beginning of the chapter or the section where you're studying One Unknown, and equations, which you should work on more at the end. If you can do them at the beginning, that's all to the good. But let's look at the expressions first. 7 increased by 12. So increased by is adding. So 7 increased by 12. This would be 7 times 12. This would be 12 decreased by 7. This would be negative 7 decreased by 12. So 7 increased by 12 is this. Check, we win. New problem. 4 less than 9. Here's what I was talking about in Alice in Wonderland. This than, less than, should set off an alarm in my brain. I'm going to subtract 4 less. We're going to subtract 4, but we're going to start with the 9. 9 minus 4. And we win. Sometimes you're called upon to translate words like consecutive integers, consecutive even integers, and I'd like to talk about that. I have a number line up here so we can look at the number line. I also have sort of a mock floor. When I first started teaching, there was a tiled floor like this with alternating colors, and it seemed to help me teach consecutive even and odd integers. So I'm going to use that here. So let's just talk about this for a minute. If we look at one of these integers here on the number line, say we look at 1, and then we want consecutive to that, means it falls right after that. If you had 3 consecutive integers, they'd be like this. And so say we represented the first one with an x, then the next one would be an x plus 1, and the next one would be an x plus 2. Hope that makes sense to you. So just like on this tile floor, if this box was x, this next tile would be x plus 1. This block would be x plus 2, 2 blocks away. This would be x plus 3, and so on. I'm going to undo that. I hope you see that. Magic. Now, what if they said consecutive even integers? Well, let's pick one of these right here to be a consecutive even integer. Let's start with right here. Let's call that one x. The next even integer would not be 1 away, it would be over here, and the next even integer after that would be here. So this would be not x plus 1, but this would be x plus 2 if we're doing even integers, and this one would be x plus 4. You could see that in the tiles as well, like if this one were x, the next even one would be x plus 2, and the next one would be x plus 4, and so on for consecutive even integers. Got that? Good. Oh, you can replay that if you need to do that again. I'm going to, by magic, remove all this stuff. And now we want to talk about consecutive odd integers. Now, when we see odd integers, a lot of times kids think about odd numbers. But let's think about consecutive odd integers. Let's say our first integer we're dealing with was an odd integer, and it was 3, and we called that x. How far apart is the next odd integer? It would be over here at 5. How far apart is this? 2. Oh, this is what's hard for kids to see, that the odd integers are 2 apart. And the next odd integer would be x plus 4. So this sometimes bothers kids, that the consecutive even integers are x, x plus 2, and x plus 4. Let's look over here. This is an odd integer. The next odd integer would be 2 away. And the next one after that would be x plus 4. So in summary, if we wanted to talk about consecutive integers, we're going to go x, x plus 1, and x plus 2. But if we're going to do consecutive even or consecutive odd, it's x, x plus 2, and x plus 4. If you have to think about this for a while, it would be really good to pause this and think about it. You might want to look at this and see that till it makes sense to you. The consecutive odd integers are an even number of steps apart. Odd, isn't it? Yep. Now we're going to look at the program and see how these translate when we actually run into the program. Thanks. The sum of 3 consecutive integers. Remember those tiles? We had x, x plus 1, x plus 2. There they are. 9 increased by 11. 9 increased by 11. Check. I'm going slowly enough that you could, if you don't have the program or haven't seen it at Howe-Two.com, you could still sort of think through the problems in your head. 7 increased, back on the last problem. 12 increased by 3. 12 increased by 3. We win. 2 less than 5. Less than alarm. Alarm. Start with the 5. 13 decreased by 7. 13 decreased by 7. 11 more than 3. 11 more than 3. 11 more than 5. 11 more than 5. 5 times x decreased by 7 times y. We get some can say 13 less than 11. 13 less than 11. 7 more than twice a number. 7 more than twice a number decreased by 6. 7 more than twice a number. 7 more than twice a number decreased by 6. The sum of 3 consecutive odd integers. Bump, bump, bump. They're 2 apart, remember. Three less than 6. Start with the 6. 3 less than 6. 3 more than, so that the 3 is going to go on the end. 3 more than twice a number decreased by 7. Twice a number decreased by 8 more than that number. Twice a number decreased by 8 more than that number. Now let's look at equations. This is starting the same thing except you set up the equation. 6 less than 9 times a number. I probably need to bring up a paint program to do that. Let's see if I can do that. Let's see. 6 less than, so that's going to be 6 less than what? 9 times x. And is an equal mark. Negative 51. Now, if you've worked the practice problems for solving equations, we should be able to add 6 to both sides. That's going to be negative 45. And 9x is equal to negative 45. So it would be negative 5. So I'm going to come up here, put negative 5 in, and check. We win. Let's do one more. Find the smallest of 3 consecutive integers whose sum is 24. Let's delete that last problem. Find the smallest of 3 consecutive integers. So if we did 3 consecutive integers, the first one would be x. The next one would be consecutive. See, it doesn't say even or odd. So the next one would be x plus 1. And the next one would be x plus 2 equals 24. Here I am drawing with the mouse instead of drawing with the pen. What am I thinking? So now let's look at this. We gathered together the things that can go together. There's 1x, 1x, 1x. So that would, adding up the like terms, that would be 3x. Add up the constant numbers, plus 3 equals 24. Subtract 3 from both sides. 3x is equal to 21, and x is equal to 7. I hope my dog is waking up, so let's see if we can't get that answer in before she starts to bother me. Thanks. We win. Practice this program, and it'll help you. Thanks. Bye.